Okay, let's work problem 10.19. The question reads, there are 3 species in this list, A, B, and C, that do not obey the octet rule. We're supposed to draw a Lewis structure for each of the compounds and state the type of octet rule exception. The compounds which are listed are shown A, B, and C. You should know choice B is actually an anion. It's a negatively charged ion. Alright, so how are we going to determine what type of violation of the octet rule exists, if it does exist? Well, the first step for always doing that is drawing the Lewis dot structure. You have to come up with the Lewis structure, okay? This is a crucial skill for you on this chapter, because real soon we're going to be predicting molecular shapes. You cannot write Lewis structures, you can't write molecular shapes, so you got to master this. Remember, what are the steps for coming up with a Lewis dot structure? The first thing that you need to do is to add your valence electrons. Your valence electrons, those are the ones in the outermost shell, highest principal quantum number. Those are the ones used in chemical bonding. Those are the ones that we can share or transfer, so on and so forth in chemistry. That's where chemistry happens, those are valence electrons. Now, how do we figure that out? Well, we have to consult the periodic table for each element. Okay, now for the element boron, that's element number 5, Z equals 5. Okay, you can see it's right next to carbon, right to the left of carbon if you can consult your periodic table. And boron, as a result, has 3 valence electrons. So when I write 3e, I'm talking about specifically valence electrons in all these cases. Okay, so it's got 3 because it's in group 3a. All right, now what's the other element here? Hydrogen. Well, we know hydrogen is Z equals 1, atomic number 1, and it's only got 1 s electron for each hydrogen atom. So now they've got 3 hydrogen atoms. Each atom's got 1 electron. Okay, so as I look at this, I sum a total. My total is 6. I've got 3 from boron, and each hydrogen brings 1 to the table. Now, you may have already kind of noticed a little bit of an issue, right? We talked about this octet rule, meaning 8 electrons each atom, other than hydrogen. Hydrogen only needs 2, but other atoms like to have 8, okay? This is a problem, because we've only got 6 total, so it looks like there's going to be a little bit of a deficiency, and I think that's going to be the case, okay? But after you add your valence electrons, you move to the second step for writing your Lewis dot structure. And that's to put or figure out what the central atom is. Now here I have no choice what my central atom is. It's got to be my boron, because hydrogen can never be a central atom. Hydrogen is never, ever, ever a central atom because it can only form 1 bond. Okay? But the second step is always figuring out what your center atom is. It's never hydrogen. So what is central atom? It's never hydrogen. It's never fluorine. And generally speaking, it's the least electronegative atom that you have to choose from, okay? But here it's going to be boron. And the step after that, this is also a third step now, is to arrange the other atoms around the central atoms, drawing in lines for bonds. So here this is BH3, so I've got 3 hydrogens I got attached to the central boron to hold the whole cluster and the whole molecule together. And I do that with these lines, so like little tethers, right? Of course, those are our bonds in our molecule. Now remember, each line is 2 electrons. Okay, each line represents 2. And they're shared between the boron and the hydrogen. It's a covalent bonding one, okay? So we've got 2, 4, 6. This structure uses 6 electrons. Right now, as it's drawn, I had 6 available to use. The only problem with what I've drawn is my central boron does not have a complete octet. It does not have 8 electrons associated with it. It's only got 6 that are shared here, here, and here. All right, 2, 4, 6. Each line represents 2. So the BH3 molecule has an exception to the octet rule. we would say that it has an incomplete octet. I'd say, oh, BH3 is an incomplete octet. And that is the exception to this octet rule. This is the correct Lewis dot structure for BH3. We have no other option because we're out of electrons, right? We'd like to put 2 more here and complete the octet, but can't do it. We don't have those electrons to spend, okay? So BH3 is an example of a molecule with an incomplete octet. That's one of our possible exceptions to this octet rule. The octet rule is usually valid or followed, but sometimes we have these exceptions, and this problem's all about the exceptions to the rule, okay? All right, the next molecule is this one, AsF4. Okay, first step is always to sum the valence electrons which are available to you. Now, I see fluorine, okay, and I've got 4 copies of fluorine. I know that fluorine is a halogen, and halogens right next to the noble gases. Each atom has 7 valence electrons. So 4 times 7 is 28. So I've already got 28 for my fluorine contribution. All right, now what about this other element, this As? Now that's a little bit of an unusual one, right? But if you look, it's element number 33. It's right below phosphorus on the periodic table, okay? And right above phosphorus is nitrogen. And if you look at the very top of that column, you realize that you're in group 5A of the periodic table, which means that As brings 5 electrons to the table. So 5 from As, 28 from my 4 copies of fluorine. But I'm not done yet, because this is an anion, which means that this whole cluster, or molecule or ion that results from bonding these together, has 1 more electron than proton. It's got 1 more electron than it should. So I need to add that in. I can't forget that. Okay, so remember, if you're dealing with an ion, you have to account for that. If it's an anion, a negatively charged ion, you add electrons in. If it's a positively charged ion, you take those electrons out or you subtract them away, okay? So clearly, when I do my addition, I figure out that I've got 34 electrons to build my Lewis dot structure with. My next step is to start arranging the atoms. Remember, I take my lowest electronegative atom and put that in the center. Generally speaking, fluorine is never a central atom. Okay? And it's the highest element of highest electronegativity, so it likes to be on the periphery all the time. So I arrange my other atoms using my lines representing chemical bonds around the periphery. So a bond here, a bond here, a bond here, and a bond here. Okay, those are 4 bonds holding the AsF4 together. It is an ion, so I should encase the whole thing in the parentheses with a -1 charge right here to tell everybody it's an anion. And now I can start assigning my electrons where they belong. I go about building my Lewis dot structure by completing octets wherever necessary. Now, I usually start doing that with the most electronegative atom as well, which here will be fluorine. And I don't really right now need to do anything to my central atom because it seems like it's got 4 bonds. And remember, each bond represents 2 electrons. That's 2, 4, 6, 8. So really that's already got 8 associated with it. But each of my fluorines only have 2. So it looks like to me, to make the structure work, each fluorine needs 6 dots around it. Now remember, these dots are representative of what we call lone pair electrons or non-bonding electrons. Okay? And each fluorine needs to have 6 dots. Got it? Now, if I do that, 2, 4, 6, 8 with the shared pair, 2, 4, 6, 8 with the shared pair, same story all the way around. I've completed my octets on my fluorine. Now each fluorine has 8 associated if you consider the lone pairs plus the bonding pair that are shared. Okay? Don't have to be shared equally, but shared to some extent. So 8, 8, 8, everything's got 8. So it looks like this molecule is in agreement with the octet rule, okay? But let's see how many electrons we've used. Remember, you always have to check the validity of your structure by seeing how many are used, okay? So 2, 4, I'll count the lone pairs first. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, Now I'm going to count the bounding periods. So 26, 28, 30, 32. So my structure, as I have it drawn right here, has used 32 electrons. But I have a problem. The ingredients, the atoms which are used to make this, say that I should have 34. I need to use 34. And I've only used 32. So it's like I've got extra. Sometimes when you do your Lewis dot structure, you've used too many, and you got to make the double bonds, the triple bonds, right? But here I've got extra electrons. I've only used 32, and my problem is, what do I do, right? Where do I put them? Well, for elements such as AS, and this would be, generally speaking, any element that has d orbitals associated with it, or n equals 3, the principal quantum number is 3, or higher, it could be 4, 5, 6, so on and so forth. But as long as the n equals 3 for that element, in terms of its valence shell, has d orbitals available to it, those elements are kind of special, because under some circumstances, they can actually have more than 8 electrons associated with them. They can have what's called an expanded octet. So in this particular case, if you ever run across a situation where you've got too many electrons and you have to put them somewhere, look for an element, and it's usually the central atom, okay? Look for that central atom element and see if it's got d orbitals that could be associated with it, which means that it has to be at least in period 3, right? Because it has to have n equals 3. It has to have those d orbitals associated with it. If that's the case, you can actually expand that element's octet. And this is an exception to the octet rule. It's called an expanded octet. Expanded octet. So if you look closely at what we did here, all I did is I drew 2 more dots, lone pairs, a lone pair, or lone pair electrons, right here on the central atom. Now if I count how many electrons are here, it's 2, 4, 6, 8, 10. And it's greater than 8, so it's an expanded octet. Now only elements, again, in that 3rd period or beyond have this ability. Okay, so that's kind of the crucial chemical factor that you want to look for when you're deciding if an expanded octet is possible. But in some cases, that happens. Okay, that's how we treat it. Alright, so this is an example of expanded octet. Alright, so there's one more we should talk about here. The SeCl4. Okay? This process always begins the exact same way. You figure out what ingredients you got and how many valence electrons are present. Now I see again Cl, and I think, oh, Cl is a halogen. So it's got 7 valence electrons. 4 times 7 is 28. Just like we had over here with the fluorine, right? Because if you look on the periodic table, chlorine's right below fluorine. They have the same number of valence electrons. Okay? Now what about this other element? Okay, what do we know about that? Well, if you look closely at your periodic table, you'll find Se selenium right below sulfur, which is right below oxygen. That's in group 6A. So it's got 6 valence electrons to contribute. We've got 34 electrons total. Now, hopefully at this point, you see that we have the same number of valence electrons, and the formula is like this 1 to 4 thing, right? So you're probably, if you've done this a couple times, thinking that the structure for this one is going to look pretty similar to what we just worked over here, right? It's a pretty similar situation where you got the 1 to 4 ratio, same number of valence electrons. You've got a chlorine instead of a fluorine out here on the periphery, so each chlorine gets its 6 dots. Right? And how many have we used? 2, 4, 6, 8 bonding electrons. So each line corresponds to 2. So 2, 4, 6, 8 bonding electrons, or electrons involved in bonds. So again, I'm just showing you where they're at, because that's important to know about these Lewis dot structures as well. Okay, differentiate between lone pair and bonding electrons. That's an important skill. We throw around that terminology a lot, but sometimes I guess we don't explicitly define what those are. But it's important to realize what I'm talking about. The lines are 2 electrons and they're representing a bond, okay? Now these dots are the lone pair electrons. Lone pair. Kind of like Lone Star, right? But this is this lone pair. So how many of those do we have? Well, we have 2, 4, 6. Each chlorine's got 6, right? So 8, 10, 12, 14, 16, 18, 20, 22, 24. If I sum up the electrons that I've used 32 in my structure as proposed. Again, we have a problem. We have 34 based on our ingredients. So we need to put 2 somewhere else. They can't just disappear from the universe, right? So can we do the same thing and put an extra lone pair on our central atom? Are we allowed to do that? Remember, how do we assess that? Well, we look at the central atom and where it's at in the periodic table. If it's at least in the 3rd period or has those d orbital electrons associated or available to it, then it's allowed. Sure enough, in this case, we see that selenium's below sulfur, so it's far enough down the periodic table to meet that criterion. And sure enough, we can just add 2 extra electrons there, or an extra lone pair of electrons on the central atom, and that gets us to where we use 34, and we're in agreement with what we had. Okay, so we had instead of 26 or 24, now 26 lone pair of electrons, and now we've used 34 in our structure. Everything checks out good. Okay. Again, this is an example of that same violation of the octet rule. That's called the expanded octet. It's when your central atom has more than 8 electrons associated with it. That's the expanded octet. Can only do that for a 3rd period element or below on the periodic table. The other case we had here was for the BH3 earlier. That was part A. This is where we had the incomplete octet. The incomplete octet is where we had less than 8 electrons on our central atom. You'll also see that from time to time. So the moral of the story is that when you're making your Lewis structures, in a perfect world, every atom is going to have its complete octet except hydrogen, which only needs 2. It's duet. Okay? Hydrogen gets 2, but other atoms would like to have 8. But in some cases, there's exceptions. Okay? Now, again, we show you this example problem to familiarize you with this as a possibility. There are, in some cases, exceptions to the rule. And you should expect to see that on quizzes, exams, and so on and so forth. But don't be scared by it. In some cases, like BH3, that just comes up, and you're required to only have 6 around the central atom. That molecule can still exist. Maybe it's very reactive, perhaps, and oftentimes that's probably going to be the case. But nonetheless, it's just an exception to this octet rule. In other cases, we can have expanded octets. But now that we work through this problem, I hope that you familiarized yourself with this, and you won't be sort of frightened or confused by it if you see it on an exam, okay?